Okay, we're going to be looking at the next chapter, which deals with stars and galaxies. We're going to be looking at observations of the night sky. We're going to talk about the brightness and colors of stars and what we can learn about those stars from that. We're going to learn about something called the Hertzsprung-Russell diagram, which is a way of characterizing different stars or stars as they are during their life cycle. And we'll actually talk about the life cycle of stars. And something you may have heard of before, black holes. If you're not really sure what a black hole is, we're going to learn about that. And we're going to talk about how stars form collections into what we are called galaxies. Now, when you look up at the night sky, you see a bunch of stars. In fact, if you're someplace where the sky is really, really dark, you can see a few thousand stars with your naked eye. That means without using a telescope. Now, if you live in a city or someplace with a lot of street lamps and buildings and things, you won't see as many stars because of what's called light pollution. That is, the light coming from the cities is bright enough, even at night, especially at night, to sort of overwhelm the brightness coming from the stars. So you don't see the stars as bright, and you don't see as many stars because you can't see the dimmer stars at all. But if you ever drive out way into the boondocks where you're really, really far away from any city, you might be startled by how bright the stars are, which is kind of a cool thing. If you ever have the opportunity to go out somewhere and really see the night sky, I really recommend it. It's really beautiful. Now, the stars, as they appear in the sky, are oriented randomly. They are not in any kind of particular pattern. But human beings have the ability to see patterns. We look for patterns. It's how we learn about the world. And so, even though the stars don't have any intrinsic patterns built into them, we sort of superimpose patterns on them, and we call those patterns constellations. And constellations are just groups of stars that form into a kind of a picture. And so one of the most famous constellations is called Ursa Major, which stands for the Great Bear, or the Large Bear. Ursa means bear, Major means great or large. And also, as part of Ursa Major, you can see the collection of stars known as the Big Dipper. And so you can kind of see, this looks kind of like a pot or pan or something that you might scoop up water with. That's the Big Dipper. Now, why do we do that? Why do we superimpose these pictures and patterns on the stars in the night sky? It's because it makes them easier to recognize. When you look up at the night sky, if you can see this pattern of stars, you can say, oh, that's the Big Dipper. That's where that collection of stars is. And there are many, many different constellations. And, if you learn a few constellations and, where they are relative to one another, it can be really easy to go out in the night sky and sort of find what you're looking for. Now, if you go out and look at the sky in, say, August, and you go out and look in the sky in December, you will see different constellations out in the night sky. And so, as the Earth is moving around the sun, the stars that you can see change from month to month. One interesting thing about the Big Dipper in particular is that the two stars that make up the end, if you line them up, the line that they make always points to the North Star. Now, the North Star is a very special star. What makes it special is this: it doesn't move in the night sky. In other words, if I go outside tonight and I look at the Big Dipper, it's going to be in a particular position in the night sky. So maybe I go out and it's over there. If I watch it, though, over time, it's going to move position. So later that night, it might have moved to over here. What's actually happening, though, is that the Big Dipper isn't moving. The Earth is rotating around its axis. So you're on the Earth down below looking up at the Big Dipper, and the Earth is spinning. And so as the Earth spins underneath the Big Dipper, it looks like the Big Dipper is moving across the sky. Now, if you're looking at the Earth has an axis about which it spins, and the North Star is basically right above that axis. And so no matter how the Earth spins, the star isn't going to appear to move in the night sky. And the star is pretty much due north. So if you go outside and you get a compass and you orient yourself pointing towards the north and you look up from the horizon, you're going to run into the North Star. That is, your vision will look straight at the North Star. And how far above the horizon is it? Well, the angle that it makes with the horizon corresponds to whatever your latitude is. So, the equator is at 0 degrees and the North Pole is at 90 degrees. And if you are looking at, if you're in New York City, for example, you could figure out what the latitude is in New York City, and then you could look up from the horizon that angle, looking due north, and that would be where you could locate the North Star. Now, one thing that is important to be aware of is the fact that all the stars we see in the night sky are different distances from the Earth. It wasn't always realized to be true. People in ancient times, they imagined that all the stars were the same distance from the Earth. So they imagined, there's the ground and there's this big sphere around the Earth, and that all the stars and the sun and the moon and everything was kind of painted on this sphere and this sort of dome over the Earth. But in fact, we now know that the stars are not all the same distance from the Earth, but they're different distances. So instead, here's the ground, and there's one star up there, and there's a star there, and a star there, closer, further away. And so you can see in this figure, for example, the stars that make up the Big Dipper, the one at the tail is 93 light years away. The one that's next to it is 69 light years away, so it's closer to us. And you can see the different values of the distances in this figure. Now, this is sort of a time-lapse exposure, and so the Earth is basically rotating underneath these stars, and so if you let the camera expose for a long time, you can see that the stars, they make tracks, and you can see those tracks are showing sort of a circular path as the Earth is rotating out from under them. Next, we want to learn about what we can tell about a star based on its brightness and its color. Now, the star's color indicates its temperature. And you might remember from an earlier lecture that we talked about how the color of light depends on its frequency. And so we can say that the frequency is related to the temperature. And that gives us that if I look at a star and it is a particular color, that color can be used to determine what the temperature of that star is. Now, we also talked previously about how blue light is more energetic than red light, and we can see that if a star is red, it's going to tend to be cooler than a star that is blue. In fact, a blue star is going to be almost twice as hot as a red star. And we know that because blue has almost twice the frequency of red light, which also tells us that the blue light has more energy in it. And so the main takeaway here is that the color or the frequencies of a star is related to its temperature. So we can actually tell how hot a star is by what color it's giving off. Now, here is a quick question. Which of these stars radiates light at the longest wavelength? And if you remember, as you go from the spectrum, that the energy is increasing as you go towards the blue and the violet. So the energy is increasing that way, but the wavelength is going in the opposite direction. Energy and the frequency are increasing, but the wavelength is decreasing. So that means that red has a longer wavelength than violet or any of the other colors. Red is the longest wavelength because as you go more towards the red, that means the longer wavelength is increasing. As you go more towards the violet or the blue, that means that the energy and the frequency are increasing. And remember, frequency and wavelength, they're inversely proportional. The frequency goes as 1 over the wavelength and vice versa. So, long story short, the answer to the question is that it's a red star. And that's not really so much an astronomy fact as just a physics fact, that red light has a longer wavelength than the other colors. Now, when we talk about the brightness of a star, there's 2 ways that we can discuss the brightness. One is the apparent brightness. And the apparent brightness is how bright the star seems to us. If I take a lighter and I light the lighter and it's right in front of your face, it's going to be pretty bright. But if I start walking away down a long hallway, the further I get away from you, because the light's spreading out in every direction, it's getting less concentrated when it reaches you. The further away the light is, the dimmer it will see, the less bright it will see. And so there are 2 factors that come into play. When I look at a star in the night sky and I see how bright it looks, it depends on 2 things. It depends on how bright it really is, and it depends on how far away it is. So if a star is dim, it could be because that star is just not very bright, or it could be because that star is very bright, but it's just really far away. And so when we talk about how bright a star is, we often will talk about the apparent brightness, and that's just how bright the star looks from Earth, how bright it seems to us. Now, the actual brightness of the star, or the intrinsic brightness, is called the luminosity, and that's how bright the star really is. And very often when we talk about the luminosity of stars, we're comparing them with the luminosity of our star, the sun. All right, here's a quick example that we can think about. So if we call the luminosity of the sun as L sun, if we were on a spaceship twice as far away from the sun as the Earth, would its brightness look more bright or less bright? And how much so? Would it be the same? Would it be half as bright, a quarter as bright, or even brighter, 4 times as bright? Well, we know it's not going to be the same, and it's not going to be brighter if we're farther away, and so it's either going to be a half or 1/4. And the answer is it's going to be 1/4 as much, because it basically goes, the brightness goes as 1 over the square of the distance. And so if you're twice as far away, the distance is twice as big. 2 squared is equal to 4, and so the brightness would go as 1/4, and that's where that quarter comes from. Now, when you're looking at different stars, you can find, if you plot their luminosity or their actual brightness versus their surface temperature, stars tend to group together in different patterns. And when you put all those patterns together, you can construct what's called a Hertzsprung-Russell diagram, or simply an HR diagram. And the HR diagram shows essentially the entire life cycle of a star. Here I've blown up the picture a little bit so that we can see the different parts of the HR diagram. Now, one of the things that's weird about the HR diagram, normally when you do a graph in math class, you might have like a y-axis and an x-axis, and the numbers are getting bigger as you go over to the right, and the numbers are getting bigger as you go up. Well, on an HR diagram, on the x-axis, or the temperature axis actually, the numbers are getting bigger as you go to the left. So you can see here it's 3,000. I'm going to the left at 6, 10, 30,000. So the temperature is actually increasing as you go in the backwards direction. And the reason they do it that way is based on some history that I'm not going to go into, but just be aware that that's an unusual way to do a graph. Now, if we look up, we can see the brightness. So here we have at the bottom not very bright, that's 10 to the minus 5. This is compared to the sun. And up here, this is 10 to the 6, so that would be 1,000,000 times brighter than the sun. Down here would be 1,000,000 times less bright than the sun. And right here at 1, that would be the brightness of the sun. And as you go over, you can see that runs right into the sun. Now, most stars fall along a line, and that line is called the main sequence. And so the vast majority of stars in the night sky fall on the main sequence. And you can see, we mentioned already that the different colors of stars correspond to different temperatures. So you can see if a star is about 3,000 Kelvin, it's going to be red. If a star is about 6,000 Kelvin, it's going to be more yellow. If a star is 10,000 Kelvin, it's going to look more blue. And even higher, it's going to look more blue. And so I can pick a star and say, take this star, and I can go over and say this particular star and this is an actual star in the night sky, I've plotted it on this diagram. This particular star is 10 to the 3, or 1,000 times as bright as the sun. And I can scroll straight down and see its temperature is, between 10,000 and 30,000. So, maybe 18,000 degrees, something like that. We can figure out, exactly what it is. And that's the basic idea. So this plot tells you, the different brightnesses and different temperatures of the stars. And you can see also some stars tend to group together. So there are the main sequence stars that we've already talked about. And there are the giants, which are very, very large stars. And then there are supergiants, which are in this part of the graph. And then down below are the white dwarfs. And so these are just different classifications of stars. And they come about because they exist in different locations on the HR diagram. So what else do the different parts of the HR diagram tell us? They tell us about what's called the life cycle of the star. Now, to understand how the life cycle of a star works, you have to understand that most of the stars in the night sky are made out of hydrogen, mainly out of hydrogen. Some of them have other things in them, but mostly they're made out of hydrogen. And the stars are so big that the mass of the stars is so big that at the center of the star, there's tremendous pressure. Like, if you go to the bottom of the ocean, the pressure at the bottom of the ocean is much higher. Well, imagine what the pressure at the bottom of a star is. Not the bottom, the center of a star. The pressure is so great that it pushes the atoms together and it creates nuclear fusion. And we know that nuclear fusion is a process that creates energy. And so what's happening is that the hydrogen at the center of the star is being fused into helium. And that process creates the energy that powers the star and gives it its radiation, gives it the light that it's giving off. Now, why there are different stars on the main sequence, that's because some stars are bigger than others. And so you can see like these stars on this end are kind of smaller. Our sun is kind of average size, and as you go up, the stars are bigger. The bigger the star, or I should actually say the more massive the star, the higher the temperature it's going to be. And so that's what we can see. So this gives you an idea of the temperature of the star and its mass. And all these main sequence stars are stars that are using hydrogen as their fuel and converting it into helium. Now, eventually what happens is all the hydrogen gets used up, and so the star at that point is made mostly out of helium, and the helium starts getting fused together into heavier elements. That produces even more energy. And so the energy is increased so much that it produces so much more energy, and it causes the star to expand. And so as the star expands, it gets bigger and bigger, and so these stars become giants or supergiants. And so often the stars start off as what are called blue giants, and as they cool off and they expand more, they shift and become red giants. So, this would be a point where the star has started fusing helium, and so it starts getting bigger and bigger, and as it expands, it cools off and becomes a red supergiant. And the same thing is sort of happening over here with the giant stars. Now, after the star has burned up all of its helium, it can collapse into what's called a white dwarf. And so we see the white dwarfs sort of end up in this region. And so you can see they're pretty high temperature, but they're very low luminosity. That means they're smaller stars, because as they've burned off all their helium, they've contracted. And so that just gives you sort of an overview of the different parts of the HR diagram.